So first of all, good evening, everyone, and welcome. My name is Natalie Walker. I'm the manager of college operations at the Classic Learning Test. I'm so glad that you found your way here, either this evening or later if you're viewing the recording. There's no pleasure like a seminar about Euclid's Elements. That was my experience some years ago in undergrad, and I hope that is your experience watching this. If you've ever studied Euclid, those that have joined us already, tell us about it in the chat. We'd love to know what your experience was. Tonight, you'll hear from William, a CLT student, who's going to help us have a dynamic discussion this evening. Thank you for being here, William. It's always good to see you.
Yes, ma'am. Thank you very much.
We're honored to have with us Dr. Graeme Bird from Gordon College in Massachusetts. He co-directs the linguistics major and minor and oversees the minor in classics at Gordon. He enjoys exploring connections between diverse disciplines such as Homeric poetry, historical linguistics, Greek mathematics, which brings us here tonight, computer programming, and jazz improvisation. Last but not least, we want to hear from you all who are with us live tonight. So please put your questions and comments in the chat, ideally for everyone to see, or you could just address the hosts. That would be me. I'll be reading your thoughts aloud for Dr. Bird, and so we can engage with them, and we're eager to hear from everyone. So with that, I'll turn it over to you, Dr. Bird. Thank you.
Thanks, Natalie. I see there's already a chat from someone that read some Euclid in 9th grade geometry. So, Sophia, way to go. I don't know if I have an accent. I mean, I do know that I have an accent. And maybe, Natalie, people could guess where I'm from and put it in chat. But yes, I came from, oh, Colleen got it. Must be really obvious. Anyway, good job, Colleen. I came from New Zealand many years ago to pursue one of my interests, which was the musical one, actually. And so I went to the Berklee College of Music in Boston to study jazz, blues, and gospel, and fell in love with the city and a young lady who is now my wife. So that's what brought me here. But I had already been a math teacher, high school teacher, and I'd done a lot of Greek and Latin. So I'm very happy at Gordon College, which is where I'm teaching full time, that I can pursue all of my interests. So I do teach linguistics, especially phonetics, which is why I like to listen to people's accents and try and figure out where they're from and have them figure out where I'm from. I do some classics. We have a small classics minor. So if someone wants to do some Latin and Greek, I'm the person to at least classical Latin and Greek to work with them. I don't teach math at Gordon College, but I do teach a couple of night courses at another job, and I do get to play piano with we have a wonderful jazz band. So we just had our concert a couple of weeks ago, and so I love being able to enjoy the things that I'm passionate about, and Gordon College allows me to do that. We have about 1,400 students, undergrads, and we have some large majors like psychology and economics and business, and some smaller ones like history and linguistics and classics, and very good education department, so people can train to be teachers and get a license here at Gordon College. And I think we have 100% job placement rate for our education majors, which is really good. So but anyway, welcome. Thank you all for being here. Thank you, Natalie, for inviting me. So and William, thank you for being there. You're our one audible and visible student, but I know there's some inaudible and invisible people out there. Feel free, as Natalie said, to send. I'll be asking some questions, so feel free to send her messages in chat, and she'll relay them to me. So, and I was thrilled to find out that Natalie has read some Euclid in her college days, so that's really exciting. So let me share my slides and we can jump right into this. Natalie, tell me if I'm doing this right. Can you see them?
Yes.
Okay, and now here we are in play mode.
Great.
So Euclid and the Platonic solids. So obviously the fact that I'm talking about Platonic solids means that Plato must be involved somehow as well, as he is. Also, the fact that I have Platonic solids in double quotes tells you something. William, what does that tell you?
That there is some question as to what the nature of the Platonic solids is.
Very good, yes. It's like the golden ratio, which is always in quotes because the Greeks didn't call it the golden ratio. It's just modern people that want to sell books call it the golden ratio because it's a cooler title. But anyway, okay, so I don't know how much math you all know or love or have tried to forget. So here's a tiny bit of review, nothing very fancy. Okay, I'll just figure how to. So I don't expect anything here to be a surprise, but here's a triangle, a square, and a pentagon. But just a little bit of the language. William, I'm sure you know what equilateral means. Could some other folks, can you put in chat what equilateral means? Just because that'll be an important word tonight. And Natalie, if anyone...
Yeah, we got equal sides.
There we go. That's it.
Yes.
So this is a particular triangle. All of its three sides are the same length. This is a square, and you don't need to say equilateral because square means all of its sides are the same length. Pentagon, you do need to say equilateral and you need to say equiangular because I wanted to have the same, all the sides to be the same, but I also want to have all the angles the same. And it's possible to squish a pentagon so that it has the same lengths of sides but different angles, and we don't want that. We want all these three to be what's called regular. So these are the only three two-dimensional shapes we'll be looking at. And a little bit of vocab. So two-dimensional shapes all have corners, but we're going to think of them as vertex or vertices. Okay, and then two-dimensional shapes have sides, but we're going to be using the word edge when we get to 3 dimensions. So I don't want to be too ambiguous. Okay, and then triangles have 3 angles, squares have 4, pentagons have 5. The little angle marks are not very classy, are they? But anyway, could I get in chat, what's the angle? What would the triangle's angle be? What would the square's angle be? And what would the pentagon's angle be? So 3 different angle sizes. 2 of them are easy and 1 of them's not. So Natalie, if you can let me see, what have I got? Okay,
Right,
Colin,
first,
2 out of
yeah.
3. Colleen, the first 2 are right. The third one is trickier. The one, let's see. Yes, John, 108. Colleen, by the way, 120, that would be the inside angle of a hexagon, but we're not going to do hexagons. That's for like beehives and things. But yes, 108. So John, yes. By the way, I once went to the Pentagon in Washington, D.C., and I thought I'll take a photo of it to show my students. And then I failed to see there was a sign saying no photography. And then I got yelled at by this guy in military fatigues and a giant weapon. So I thought, oh, I did something wrong. Anyway, I managed to not cause too much trouble. Okay, so here we go. So so here's the angle 60, 90, and 108. Okay, let's keep going. Okay, so part of ancient Greek math is imagination. So can you all imagine, maybe you shut your eyes or not and imagine a cube? This is maybe the most common Platonic solid. And then I'm going to ask you if you can visualize how many faces that's like not we don't call them sides, we call them faces. How many corners and how many edges? And the first one's the easiest. If you're imagining a cube, how many faces? And you might think of a die, the singular of dice is die. So 6 faces. Melissa, yes, good. And then corners or vertices. How many corners? So you're supposed to try and do this with your eyes shut, seeing it in your mind. 8, Josephine, yeah, good. And then edges. William, you could contribute if you like this one.
This would be 12.
12. And Ray as well. Yes, good. So 6, 8, and 12. And actually there's interesting relationship between these 3 numbers, which I think we won't get into tonight. But the Greeks loved geometry, shapes, imagining things, number theory, whole numbers, patterns. There's even musical connections. And as a musician, I'm fascinated by the way they applied this to music as well, but that would have to be for another time. So yes, 6 faces, 8 vertices, and 12 edges. And a die would be the most obvious one. Okay. I'm a huge fan of the ancient Greeks. Here's some of my favorites. Homer. By the way, William, can you see the mouse as I'm pointing? Is that?
Yes, sir, I can.
Okay, good, thanks. So Iliad and Odyssey, I got question marks there because there's a lot of argument about that. In fact, my PhD was on Homer, so I won't get into that tonight, but keep going for another few hours. Herodotus, sometimes called the father of history. Thucydides, a little bit after Herodotus, but also a historian. Greek tragedy, the big 3, Aeschylus, Sophocles, Euripides. So you might have read Oedipus Rex or Antigone or one of those. Aristophanes, the sort of main Greek comic playwright. Plato and Aristotle, lots of philosophy plus, meaning that Aristotle wrote about just about everything. And then the 3 of the big Greek mathematicians, Euclid, Archimedes, and Apollonius. So these are some of the most famous ancient Greeks, and the Greeks have contributed so much to our civilization, which is why they've fascinated me for so long. Now, Pythagoras and Socrates were not on the list. Can anyone tell me why? Why, even though they're really important, why did I not have them on the previous list? Apart from the fact that I couldn't fit everyone in.
Because I believe they are the ones that have no surviving writings, as Colleen says.
Yes. So, Lisa, actually, that's interesting that you say they. Oh, LOL. Okay, I'm trying to get the joke. No, algebra is a wonderful thing, but the ancient Greeks didn't seem to have algebra in the way that we have it, like X's and Y's. And so, but they did have geometry. As William said, Socrates did a lot of talking, but he didn't write it down. Plato wrote down the things that Socrates said. And so we say that it's Plato's writings that talk about Socrates. Pythagoras is kind of even more mysterious. We presume he did a lot of talking, but no, he didn't write it down. Some people think he had a secret society, and some people gasp, don't even think he existed, but I'm a believer. A strange fellow though, but anyway. So let's keep going. Okay, so I'm going to focus on Euclid, but I'm going to mention Pythagoras and Plato a little bit, and I'm also going to keep track of the time because I don't want to. Just want to manage things well. So Pythagoras, mysterious. We think he lived about 570 to 495. Believe the universe was created out of numbers. I really like that, actually. Other early people thought it was made out of fire or water or air, but Pythagoras thought it was made out of numbers, which is a whole different kind of thing. It seems like Pythagoras knew about the regular solids that weren't called Platonic solids yet. And then comes Plato a bit later, and he thinks, he thought that the world, what we see in the world, is only an imitation of the real ideal world, which is somewhere out there. And he also wrote, we'll read some of what he wrote about the regular solids. And he didn't call them Platonic solids either, because that would be sort of narcissistic, I guess. And then Euclid flourished, meaning we don't know when he was born or died, but he kind of blossomed around 300 BC, reached his kind of strength. And he analyzed the regular solids. And we're going to end tonight with his proof that there could only be 5, no more than 5. And I think that's kind of cool. So here we go. Now, one other Greek. So my next handful of slides will have a bit of text, and we won't read all of it, but I'll point out the high points. So Proclus, now he's in the AD era, so he's hundreds of years later, and he's trying to write about where did Greek geometry come from. And when you're writing hundreds of years after the fact, you know, how do you even know? So we take it with a grain of salt. But Proclus says that the Greeks got geometry from the Egyptians. And the reason is, this is interesting. I don't know if any of you have been to Egypt, but most of the ancient Egyptians lived near the River Nile, and it would flood every year, and your property would get flooded. And so the boundaries of your property would disappear, and you have to be redrawn and I guess for taxes, they had to recalculate how much land people had so they could charge them taxes. And so that seems to be one of the origins of geometry. The Egyptians are remeasuring each person's land after it's flooded. So that's kind of interesting. Okay, Proclus goes on and he says about Pythagoras, and he says he changed geometry. And I like things like theorems abstractly and purely intellectual. He says we're not going to just use geometry just for practical purposes. We're going to do it intellectually. We're going to kind of think about it in our mind and imagine things. So taking it from just what you can see and touch, which you might call empirical, into more abstract and intellectual. And where it says here liberal discipline, you've probably heard of the phrase liberal arts or humanities. So maybe Pythagoras is what really got the idea of the humanities started. So that's dear to my heart, and I'm sure to many of yours. Also, he ends with the cosmic figures, which many people think sounds like it's the Platonic solids, even though they weren't called Platonic. Cosmic meaning relating to the universe. So, okay. Then Proclus said about Plato, ... means we left out a bunch of stuff here. But the last part, Plato sought to awaken admiration for mathematics in students of philosophy, meaning he didn't really do math, but he tried to get people to appreciate it. Because Plato was, you might say, primarily a philosopher, but when he's trying to teach philosophy, sometimes you can use math to help get the lesson across. So math for Plato seems to, according to Proclus, was a tool for helping people understand things like justice and beauty and piety and things like that, which is really interesting. And then our man Euclid. Now, okay, I will read this because this is kind of, let's see. By choice, Euclid was a follower of Plato, connected with the school of philosophy. He set up as the goal of the elements. This is the thing that Euclid wrote that we're going to talk more about. He set up as the goal of the elements the construction of the so-called Platonic figures. Aha, we're finally getting a mention of the word Platonic figures. Now here we get, I think, what's a rhetorical question. If you seek, actually, William, would you like to read this? Middle?
Sure. If you seek to add or subtract anything from Euclid, are you not unwittingly cast adrift from science and carried away toward falsehood and ignorance?
That's pretty powerful stuff, right, William?
Absolutely.
And then let me read the last one. His elements contain the complete and, how about this, irrefutable guide to the scientific study of the subject of geometry. So Proclus has a view, well, let me ask you, William, what do you think, what did Proclus think of Euclid based on what we just read?
I would say he considered him the ultimate authority on geometry.
So this is here's an abstract Greek symbol. No, it's not an abstract Greek symbol, but this means I think Proclus really loved and admired Euclid. When you say that if you add or subtract anything, you're going to get in trouble, that means you think he's the cat's pajamas. You say that expression, William, the cat's pajamas?
Oh, all the time, of course.
Okay. I only say it occasionally, but anyway. Okay, so let me just take a sip of my nectar, which is actually coffee. Nectar was what the gods drank, but that's another story. Only second to the Bible in the number of editions published. So over 1,000 editions of Euclid, and I don't know how many of the Bible, but apparently more, was translated into Latin, Arabic, and Hebrew. I've tried to read a bit of it, and I can read it in Latin. I've tried to read a bit in Arabic, but I need to work more on my Arabic. But the Arabs helped contribute algebra to math, but that was after the Greeks. So the Greeks didn't really have the kind of algebra that we have now. And Euclid is still in print, and I recommend, Natalie, do you remember, I don't know if you're there, Natalie, do you remember what edition of Euclid you used? Oh, was that you holding it up?
Yeah, this is the Green Lion. This is what we use.
Oh my goodness. Oh, and can you hold it up one more time? I recognize that that's from Raphael in the Vatican, right?
That's right. Yeah.
That's a beautiful fresco, and it has Pythagoras on the left and Euclid on the right. Oh my goodness. Yeah, lovely. Thank you, Natalie. That was perfect timing. Okay, so now we need to see, if you write something called the elements of geometry, what are elements? And here's a possible etymology. I'm a big fan of etymology, but not entomology. That really bugs me. So one theory is you have ABCs. If you start in the middle of the alphabet with L, you have LMN, and maybe that turned into the word element. Some people think that might be true. And I was just checking that today. People aren't sure where the word element comes from, but this is one theory. So I kind of like that. And then what is geometry? So if you know Greek, you'll know that geo is the prefix meaning earth, like geology, study of the earth. And this is from the verb to measure. So geometry, measuring the earth. So that goes back to the Egyptians, right? As Proclus already said, but we can take it a lot further than that. Okay, let's think about dimensions. Let me just see, I got something in chat. Oh, Sophia, School of Athens. Sophia, have you been there? And if not, you should. It is beautiful. So, Sophia, let me encourage you to go when you have a chance. It's in a room. It has 4 frescoes on the 4 walls, and the most famous one is this. And Sophia, you probably know that it has Plato and Aristotle up in the center, and Plato is pointing up, meaning that reality is somewhere up there, transcendent beyond the world. And Aristotle is pointing down, meaning, no, it's here. And so Aristotle was the student of Plato. Yeah, good. Then if you turn to the other walls, there's the theologians wall. I think it's opposite the right, the philosophers, and then there's the lawyers wall, and then there's the literature wall, which has Homer and Dante and Virgil. So you could spend a couple of hours there. It's just, you've got to get rid of the tourists, that's all. No, I don't mean get rid of them. I mean they're it gets kind of crowded. Yes, I agree. Art history is wonderful. Okay, so let's get a little mathy. So we start with 0 dimensions. And so, William, I'm sure you know this. Can folks in chat, think of something that has 0 dimensions, that has no width or length or depth? And you might think, well, anyway, what do you think? Let's see. Kimberly, yes, a point. Because a point well, it doesn't have size. And so, okay, I got this off the web somewhere. Here's the point A. It's a very fat point, so it looks like it does have length and width, right? But that's just so you can see it. So, Kimberly, yes, until you draw it, if it has no size, then it'll be invisible. And here's Euclid's very, very first definition in his Elements, which is a point is that of which there is no part, which is a fancy way of saying a point. You can't break it up into smaller pieces. By the way, can you see my background?
Yes, it's lovely.
Yes. Natalie, do you know what it is? I'm trying to get out of the way.
It's the first proposition, is it?
It is. Oh, you remember this well, Natalie. So what has he just shown us how to draw?
An equilateral triangle.
Yes, and it's two circles. It reminds me of the MasterCard logo, but I'm not sure if there's a direct link. But yeah, this is from a 1,000-year-old Greek manuscript, also in the Vatican. And it's freely available to see online. And I thought, what better background than Euclid, Book 1, First Proposition. Here's how to draw an equilateral triangle. So it's in the Greek is not printed; it's handwritten, so it's quite a bit harder to read than printed Greek. But okay, so let's see. So there's our the first thing that Euclid starts geometry with, a point, the simplest thing there is. Okay. So let me ask someone else on chat. It'll be easier from there, right? What kind of things only have one dimension, just length? So let's see. A line, yes, Ray and Sophia, yeah. And so here's the thing. When Euclid says line, he means it could be curved or straight. When modern people say line, they mean a straight line by default. And so wherever I got these things from hunting around the web. So here's a straight line. And in modern math, 2 points define a line, and it can go infinitely in either direction. So these are, Euclid didn't see it exactly like that, but he saw it as a line segment, which you could extend if you wanted to. But anyway, Euclid, a line is length without width. That pretty much agrees with modern dimensions. Okay, William, what's coming next?
2 dimensions, which would be a flat shape.
It would, length and width. And again, it could be curved or plane, which means flat. I just did a drawing of a flat one because it was extending my drawing skills. When Euclid says a surface is that which has length and width alone, he's allowing for a curved surface as well. If he wants it to be a flat surface, he'll say a plane surface. He'll use the word plane. So I'm trying to give the 2D impression here with my little PowerPoint drawing. Then, of course, we got 3D, length and width or depth, or sometimes, and depth. Sometimes people say height. And so here's my attempt at drawing a 3D solid, we would call it. And then I'd put the dotted lines for the ones that are in the background just to try and make it easy to see. And here's Euclid's definition of a solid, that which has length, width, and depth. So you can see that Euclid's definitions pretty much work now, and I think our definitions really go back to Euclid in many ways. Okay, of course, what comes after that, William?
4 dimensions.
Yeah, what do you reckon? Can you imagine one of those?
I cannot.
So that's why I'm going to say let's not go there for now. Although there are fun videos out there, my son has shown me some, where you can do a sort of pseudo 4th dimension. It's really interesting, but anyway, we won't do that right now. Also, if you think of the 4th dimension as time, then you get into Einstein and relativity, and that's another direction. All good stuff, but not tonight. Okay, what is a Platonic solid? Because that's what we're supposed to be talking about. Here's the official definition: a regular polyhedron. Of course, you have to know what regular means and polyhedron. And polyhedron is not the kind of word that I use every day. So here's my cheeky comment, huh? But here's another definition, which may or may not be helpful. A 3D solid figure with all of its faces equal, like the cube we looked at, and all of its faces are equilateral, like the square on the cube, and equiangular. Actually, this is easier, right? So a cube is an example of a Platonic solid. It's got all of its faces, which are squares. They're all equal to each other. They all have the same sides, and they all have the same angles. So actually, I think it is easier than this, maybe. I started with this one because this is familiar to us from rolling dice, and so Monopoly and whatever other games use cubic dice. Okay. And actually, this slide, we've already done this, right? Which well-known solid has all of its faces equal? So the cube, we already did it. I read my own mind. Okay, but there's going to be 4 others that are maybe less familiar. Okay, so just to repeat what we did, right? Each face, remember we're going to use face for the sides of a 3-dimensional. They're like planes, and they're going to be all equilateral and equiangular. Okay, but let's look at the other ones. Oh, and we already did this. Just as a reminder, don't look at your formula answers. How many corners and how many edges does a cube have? William, I know you know already, but let's let someone else. And can you visualize them? This is a great exercise. Visualize a cube. How many corners has it got? Someone remind us in chat. 8 corners, yes. And then how many edges? I think Ray, you just gave us the 6, 8, 12. Yes. Good. Okay. So that's the easy one. So we're going to see all the 5 Platonic solids in order from the smallest number of faces up to the largest number. And the cube will be the second one because that has the second smallest number of faces. So this is a tetrahedron. And yeah, my images, I got them just from Googling around Wikipedia and various other places. Tetra is pretty close to the Greek word for 4. So 4 faces. So can you see, just try and visualize this. Can you see 4 triangles as the faces of this figure? And this dotted line is supposed to help sort of one of the edges in the background. So try hard. Can you see 4 triangles? And they have to be equilateral triangles because that's the only kind you can use. Can you, yes, good, Lisa. Can you see the 4 vertices? Oops, oh, cool. I hate it when I do that. Can you see the 4 vertices? Obviously, the correct answer is yes, if you can. And then you're supposed to be able to see 6 edges. So there's 3 on the bottom because the bottom is a triangle, and then 3 going up to the top. Lisa, I like your answers. That's very consistent. Yes, and yes. Good. This is the easiest one to visualize, I think. By the time we get to the end, you'll be thinking my brain hurts or something. But it's good. It's interesting. Euclid didn't use the word tetrahedron. He used the word pyramid. But what's the problem with using the word pyramid?
We usually think of a pyramid as being a square-based solid.
Yeah, I mean, the Egyptian pyramids had a square on the base and then triangles going up the side. So, William, could that kind of pyramid have been a Platonic solid?
It could not have, because that would have used 2 different types of shapes.
That's it. But I think the Egyptians weren't really interested in Platonic solids. They just wanted somewhere to bury their dead pharaohs, right?
That's right.
Yes. Oh, Lisa, what? Maybe also not flat sides. I'm not. Oh, for a pyramid? Well, I think they were supposed to be flat. I actually haven't been to the pyramids. I hope to one day. But Euclid's definition of a pyramid is something that has a polygonal base. Oh, I see what you mean, Lisa. Yes, you're right. Is that because people have peeled off the stuff on the sides or what? I'm not sure. There's
Yes,
been some
that is the
vandalism.
case.
Yeah. Euclid's definition of a pyramid is it's got to have a polygonal base, so it could be triangle, square, pentagon, and then it'll have triangular sides meeting at the top. But when he comes to refer to the Platonic solid, instead of saying tetrahedron, he just says pyramid and assumes we know which one. He assumes we know which one he means. So anyway, he's Euclid. He can do that. So we got 446. Okay. Okay, we already did this one, but just as a reminder, hex is the Greek word for 6. So a cube could be called a hexahedron, but I much prefer the word cube. I don't think Euclid uses the word hexahedron. He uses the word cube. So here's the 6, 8, 12, right? 6 faces. And can you visualize them all? I think you already can, all right, because I already asked you. The edges, you've kind of got 4 on the top, 4 on the bottom, and then the 4 vertical ones. So it's pretty systematic. By the way, a tidbit of information, if you want to, and I won't be doing this tonight, you've probably heard of the arithmetic mean, which is like the average, and you've probably heard of the geometric mean, but you may not have heard of the harmonic mean. And for those of you that want to research this later, the 8 is the harmonic mean of 6 and 12. It's not the arithmetic mean and it's not the geometric mean, but it is the harmonic mean. And to me, this is really, really fascinating. And the word harmonic suggests that there's music going on. And in fact, there are musical applications, but we'll have to save those for another time. Okay, number 3, the octahedron. So octo is the Greek word for 8. So it's got 8 triangles. Can you visualize all the 8 triangles? I think it's not too hard, right? And in fact, if you cut the octahedron in half, Lisa and William, you'd get 2 of those things we were talking about, right? What am I referring to? Oh, Sophia, yes, 2 pyramids joined at the base, exactly. But because the squares are not part of the outside, they don't count. So it's 2 like Egyptian pyramids joined at their bases. So we've got 8 triangles. And the corners, I think you can see the 6 corners or vertices. Okay, and then the 12 edges, it's kind of 4 pointing up, 4 flat ones, and then 4 pointing down. So 8, 6, 12. By the way, here's something, I don't know if I was going to have time to mention this, but I'll look at this and then we'll go back a slide for a second. So 8, 6, 12, right, for the octahedron. If I go back, 6, 8, 12. And it turns out that the cube and the octahedron are kind of, they're pairs. They're like, you can go from one to the other by doing some interesting geometry. So anyway, I'll throw that out as another idea that you can look at. Okay, now your brain is going to start working overtime. The dodecahedron. Dodeca is the Greek for 12. Do is 2 and deca is 10. So 12 pentagons. So I don't know, William, can you see 12 pentagons? You got to look hard, don't you? Oh, you're muted, William.
It appears to be 6 on each side and 1 in the center and 5 in a pentagon pattern around them.
Okay. Your brain is working better than mine, William. But yes, so 12 pentagons. I don't think I want to ask anyone to count the 12 vertices, but feel free. And then the 30 edges. I mean, yeah, I'll take it on faith. They're all in there somewhere. You can actually make these. Maybe some of you have made these out of these right pieces of cardboard and stuff. Oh, Lisa used to have them hanging. Oh, Lisa, are you a math teacher? That's wonderful. Straws. Oh, I love it. Yeah, getting your hands on these things and making them and touching them is great. And then the last one with the most number of psi. And by the way, notice 1220, and now the icosahedron 2012. So these two are pairs also. You can get from one to the other, so to speak. Melissa's had students make them. I love it. I think students like when you sort of get your hands on things. So the Greek word ikosi is 20. By the way, hedron means something like base. So it's got 20 bases. You could sit it down in 20 different ways, 20 different bases. 12 corners, probably easier to count because there's only 12, and 30 edges. I'll leave it to someone else to do that. So these two are harder to visualize, but it's all true. It's all true. Okay, let's keep going. Now, why are there only 5? And I must say, when I first checked out this proof, I thought, this is amazing. There should be lots, right? Why is there only 5? So we've got to think about something called solid angles. So here's Euclid book 11, definition 11. A solid angle is that which is contained by more than 2 plane angles, not in the same plane, constructed to one point. That sounds a little verbose. Let's just look at it. Here we go. Can you all see this picture of a cube? So here's one of the vertexes or vertices. So this is a solid angle. And what things meet at this vertex? Or how many things meet at this vertex? 3, Sophia, yes. And Sophia, what are they? What are the 3 things that meet at that corner? Well, no, no, the shapes, the faces. What are the 3 faces that meet at the point? Squares. Yeah, that's what I was that's what I'm looking for. Yeah. And what's the angle at the corner of a square? How many degrees is the corner of a square? It's one that we all know, right? 90 degrees. So what's 3 times 90? A little bit of mental math. 3 90s, 270. So the solid angle at the corner of a cube is 270 degrees. Okay. Now we're going to do all 5 of them and we're going to see what's going on. Okay, next. Can you do the same? How many things meet at the vertex, and what are they, and what's the total angle? Yeah, there's 3 of them. And what are the things? Yes, and what's their angle? This is from the way back. What's the angle of an equilateral triangle? Yes, so do the math. Yes, it's it. 180 degrees. Okay, next. How many things are meeting at a point? So we can speed this up a little. How many things meeting, and what's going to be the solid angle? 4 times 4 triangles. That's it. 4 60s are 240. Okay. Now we get a little harder. One of you got the correct angle for, so there's 3 watts meeting here. 3 pentagons. What's the angle of a pentagon? This was the tricky one. Internal angle. Yes. 3 times 108 is 324. That's it. And then the last one, how many things meet at a point with the icosahedron? And what's the total angle? Yes. Oh, someone said 6. Ray, do you want to take back that 6? 5 triangles. 6 would be a problem, as we're going to see. Yeah. So 5 times 60 is 300. Okay, so why stop there? Okay, so here's what we got so far. I'm just summarizing them here. Tetrahedron, 3 triangles, total of 180. Right, so here's the 5 Platonic solids so far, and here's their solid angles. So, William, should we try and prove Euclid wrong?
My intuition says no, that's a bad idea.
But you got to try, right?
Must we?
Well, this is me being facetious, tongue-in-cheek. Euclid claims there are only 5, so of course we know he's going to be right, but let's just see. Let's just be kind of cheeky and see if we can find another one. Should we be trying to prove him wrong? Well, whatever. So here's my new mystery solid. We already had 3 triangles meeting at a point, then 4, then 5. What if we had 6 triangles meeting at a point? That would give us a solid angle of 360. And then I got 3 asterisks there. William, do you know why I got 3 asterisks there?
Because 360 degrees would be a flat plane and thus could not create a solid.
Yes, and do you know why I say Houston, we have a problem? This is my little joke from way back.
I do not.
I think it needs us older folks. How many of you know what Houston, we have a problem alludes to?
The NASA space station in Houston.
Melissa is in Houston. Okay. Melissa, I hope you don't have a problem. This goes back to Apollo 13. Yes, Lisa, excellent. So some of you weren't, William, I'm sure you weren't around when man landed on the moon. I was in 9th grade, and even in New Zealand, they broadcast it over our loudspeakers and everyone cheered. And that was Apollo 11. 2 Apollos later, they ran into a problem, and it was made into a brilliant movie with Tom Hanks, and everything ended up okay. But so actually, it's not Houston that has a problem. We have a problem. Anyway, as William said, if you have a 360-degree solid angle, it just won't work. And you could try and imagine it. It would be like 4 squares meeting on a flat piece of paper. It's not, it's only 2 dimensions, it's not 3. So what does that mean? That means we tried to find another Platonic solid using triangles, and we failed. Let me just quickly go back. What if we tried 4 squares meeting at a point? 3 squares works. What would happen if 4 squares met at a point? What would the solid angle be? William?
360 again.
Yeah. What if we had 4 pentagons meeting at a point?
It would be 448 or 432.
Yeah. And then what if we had hexagons? Well, the internal angle of a hexagon is 120. 3 times 120 is 360, which is good if you're a bee building a beehive or a honeycomb. So all that to say, Euclid was right. Surprise. We're not surprised, are we, William?
Not at all.
Right. But it's always good to try, just to kind of, it validates your admiration for Euclid. Okay. Let's end with, okay, here's my little joke since I'm from New Zealand. William, could you say this word as you normally say it and then say this word as you normally say it?
Plato and Play-Doh.
Yeah, but I know a lot of Americans say Play-Doh for this. Do you ever?
I do not.
Okay. It's not a judgment. I'm not judging anyone. But I teach phonetics, and it's a thing about American English. Often a T between vowels becomes a D or something like it. And it's not wrong. Whatever the Brits may tell you, Americans have not destroyed the English language, so don't believe that. But I just think it's funny that for some people, the 2 words sound the same. Oh, Colleen, yes. So, Colleen, so if you want to climb up the side of a building, you use a ladder, right, with D's. But if you've got the former and the latter with T's, So Colleen, tell me if when you say latter, you say ladder, like would they sound the same? And another one is if you do a lot of writing and if you do a lot of riding, is a rider the same as a rider and rider? Do they sound the same? And I think they do for some speakers of American English. And I think that is really interesting. If you want to, yeah, you're welcome. If you want to imitate a British accent, you kind of have to undo some of those things. And you also have to take the R off. You have to say, I park my car in Harvard Yard instead of I park my, all that stuff. So I find that really interesting, actually, and I like to get a lot of laughs. As long as my students don't think I'm making fun of them. Well, I make fun of them gently. But Melissa, yeah, good. I'm glad this was interesting. Okay, so now is it Sophia that you really love Raphael's fresco in the Vatican? And I'm sure several of you do. But if you look closely, and I maybe should have included this here, Plato is carrying a book in that fresco, and it says in Italian, Timeo or Timeo. He's actually carrying a copy of his Timaeus, but it's Italianized. Apparently Raphael didn't know Greek or Latin. And so this is extra cool. So this is one of the last works that Plato wrote before he died. And here's the one Greek word in tonight's class. Maybe, Natalie, should I ask you to say this word? I'm sure
No. Theos.
What's that? Theos. Yeah. So this is actually the word for God as used in the New Testament. And Plato obviously was not a Christian or even necessarily a monotheist, although people debate about it. But he does talk about the God, ho theos. And he says the theos created the cosmos, universe. And he hypothesizes that maybe the theos used the Platonic solids. And this is why I think they're called Platonic, because Plato assigned them to the four elements. And here's the four elements. And I have to be careful not to say earth, wind, and fire, because I love that band. But this is earth, fire, air, and water. So on the next slide, I'll show you which ones he matched up. But does anyone want to guess which Platonic solid might go? Now, if you already know, I want you to guess rather than just... Any ideas which might be a good Platonic solid for any of these? It's not that easy, actually. Let's see, what do we got? Sophia, very honest. Okay. William, can you... Oh, hang on. I'll ask William in a second. Kimberly, earth cube, yes. Colleen, fire, tetrahedron. Oh, you guys sound like you're Platonists. So, William, do you want to add one? Do you know? We're going to have cube for earth is right, and we're going to have tetrahedron for fire.
I would guess that the air is the third one. The I don't remember what it's called. The double pyramid, I guess.
You're right. Yes, you are right. You are right. So cube is earth. Now here's the reasons. I'm impressed that two of you. So a cube is supposed to be the most stable and immovable, like earth. Tetrahedron is the smallest. It's sharpest because all the solid angles are only 180 degrees, and it's the lightest. And we know if fire goes up. So, he's got some good ideas here. It's not super scientific, but then if we jump to water, the 20-sided one, that's the largest and the heaviest. And I'll explain what I mean by flowingest. I made that word up for tonight. And then air is in between fire and water. So it's kind of heavier than fire and lighter than water. Oh, Sophia, wait, there's more. Sophia is saying, but there's 5. What's going on? No, Sophia, it's coming. You're totally right. But I once, in one of my classes, I had models of all of them, and I rolled them all across the classroom floor, and the icosahedron rolled the furthest. So that makes it work for water, right? Have any of you math teachers tried rolling them across the floor in your classroom? It's good on a rainy day or any day really. But Sophia was nervous that is Plato forgotten the dodecahedron, or did he not know about it? That would be embarrassing if Plato didn't know about one of the Platonic solids. So here we go. Actually, this is my last slide. Wow. Okay. Plato actually says he, the god, still had the dodecahedron. It was still one remaining. So he used it for the heavens, and you could think of the 12 signs of the zodiac, the 12 constellations, which the Greeks and Romans gave really interesting names to, which are still used, like Pisces and Cancer and all of that. And I don't know about you, there's something about the Pentagon the Pentagon is kind of mysterious. It's the only 5-sided one used here, and it's got this 108-degree angle. Constructing a pentagon involves the square root of 5, which is kind of a little bit mysterious. Even some people might say mystical. So, so Sophia, are you relieved that he didn't forget the dodecahedron? I sense that you were worried, but yeah. So at the very end of his life, Plato wrote a lot of things, mainly called dialogues, because he you're more curious than worried. That's good. That's good. You can imagine if you've had a long life, and I think he was in his 90s, and you're trying to end on a high note, and so he decides to think about the creation of the universe. He also, in the Timaeus, talks about musical intervals. So if you were going to pursue this, he would say that the creator, in another part of this book, used musical ratios and intervals that were mathematical and musical. So the whole universe is kind of like, you may have heard of the music of the spheres kind of thing. The universe is based on numerical ratios, yes, and music. And as a musician myself, I think that is pretty special. So on that note, I'm going to stop sharing. Should I, Natalie, stop sharing now?
Sure. We can see if we have any questions. Is that what you had?
Yes. And thank you for those questions and comments, and especially those of you that like the School of Athens. But everyone, yeah, thank you very much for having me. Are there any other questions or comments before we call it a night?
I just had one question. You mentioned that the main text from which all this information from Euclid was drawn was the Elements, and it seemed like that was the main source for the origin of Platonic solids, if that's correct. Would you say that it's a readable book for anyone to pick up and dive into?
You're saying Euclid, right?
Yes, sir.
Yes, and actually that ties into Colleen has a question. What is my argument for reading Euclid today? Well, actually, before I get there, Colleen also said, what did the Greeks call the golden ratio? They actually called it extreme and mean ratio, which sounds much more boring than golden ratio, doesn't it? So extreme and mean ratio. This summer, actually, I'm going to be co-teaching a course in how to read Euclid in Greek. Now, I'm not, that's not for the faint of heart, actually, because these folks in 6 weeks will have to learn enough Greek to read Euclid and Euclidean and non-Euclidean geometry. So it's going to be, so I admire them already. But yes, why read Euclid today? I wouldn't just sit down and read it from beginning to end. I would use some really good websites, resources that you could take your pick, read some, like book one, proposition 1, the equilateral triangle is pretty easy to understand, and you draw an equilateral triangle and then you prove it. He always has to prove that he's done what he said he was going to do. The proof is very accessible. Then, of course, you could jump to the Pythagorean theorem. And here's a proof that has nothing to do with whatever proof you learned in high school, because Euclid's rule was you only use things that you've already proved. And of course, he didn't have sines and cosines and tangents, so he couldn't use those. So I would read the bits of Euclid that relate to the geometry that you're familiar with today. If you really want to have your mind blown, go to the very end, book 13. He'll tell you how to draw an icosahedron using compasses and straight edge alone. And you might be thinking, well, how would you do that? It's a three-dimensional solid. I only have two-dimensional papyrus. And yet, if you follow the 3 pages, I think, of his construction. So if you want your mind to be blown and to just realize how brilliant this guy was, go to the end of the elements. One last thing, if you want to prove that there's an infinite number of prime numbers, he does that. And I believe his proof is still used today. And it's very elegant and not simple, but easy to understand. You think you've got all the prime numbers, you can always find another one. Therefore, there's an unlimited number of prime numbers. So I don't think I'd read him from beginning to end, but I would pick and choose. And I think it'd be very, very rewarding. So yes, William has a Texas map behind him. Yes, yes. I'm just reading a couple of these comments. Kimberly did see the School of Athens. Yeah, that is great. And by the way, okay, last thing, sorry. Natalie, I'm going over. Am I in trouble?
No, thank you for your time.
Underneath the School of Athens, there's 2 sort of sepia-colored engravings of Archimedes, and one is of the death of Archimedes, and people don't usually look at it because it's not in color. But I took some photos of it and I show it to my class. It's kind of sad. Archimedes builds all these war machines to keep the Romans away, and then the Romans find a way in some other way, and then they come in, and a soldier is supposed to take Archimedes to the general Marcellus. But as luck would have it, Archimedes is busy doing a math problem, and he says, "Don't bug me till I finish this math problem." And the Roman soldier didn't like that, and so euphemistically dispatched Archimedes. So that was a kind of a, that's also in the room in the Vatican, but it's less noticed. So anyway, well, Natalie, I think I should say thank you to everyone for being attentive, and turn it over to you.
Thank you so much, Dr. Bird. A great teacher, and your intellectual kind of generosity comes through so much. It was so enjoyable. Lots of thank yous in the chat to you.
Oh, someone from Bogota, Colombia. Well, thanks, Karina.
Well, my recommendation as we part is to, if you pick up Euclid to read, also present it, find someone to present it to. William has it easy. You have 5 siblings. You can you can explain it to any one of them. You're in good shape. But it really is a pleasure to demonstrate these things for yourself. Try to figure out when and how it clicks. It was really fun. This was fantastic, Dr. Bird. Thank you so much.
Thank you very much, Natalie, William, and Sophia, and all these, Colleen. I'm just looking at names: William, Kimberly, Melissa, Karina, Sarah, Josephine. Really appreciated your feedback, and all the best. I hope maybe see you again sometime.
Yes, sir. Thank you very much.
Thank
Have a
you.
good night. Thank
Okay,
you.
bye-bye.